Hello fellow skeptics, my name is Luther Name, and this is the first of a series of videos that I'm going to prepare on a broad topic of what's wrong with modern physics and how do we fix it. Now those are that's a pretty ambitious set of topics to address. In fact, I expect you to be skeptical that I or anyone else could sit here and tell you I know how to solve the problems in modern physics. I don't know that I know how to solve them all, but I have an edge, and that edge is that many years ago I discovered that we've missed something in our classical physics. And about 10 years ago I began to look at, in detail, that particular omission or error that I had discovered, and discovered others. And then I discovered others. One led to another. And so my working hypothesis is we've missed some physics. And the problem with modern physics is that we've tried to backfill those things that we've missed, and we've gotten it wrong. And that's led physics to go down a series of dead-end paths. So my goal is to provide a roadmap for how we might correct some of these issues that have arisen. Maybe not all of them, but at least a fresh approach. In reviewing the YouTube videos in terms of how to present the material that I'm going to be talking about, I was struck by the fact that the people who are reporting on science, physics in particular, are no longer participants, active participants in the physics community itself. They're like reporters, talking heads. They're basically passing on information that they've heard or read from other sources. But they themselves are not participants in trying to solve the problems. And given the state of modern physics, I don't know that anybody's really able to solve those problems. We get new hypotheses, but they're the same old thing that we've looked at before, that the theoreticians who are looking at some of these things, the astronomers or the observational physicists, are seeing things, trying to explain them, and the theoretical physicists are not doing us any good. They go back to the same old well, or they make hypotheses that they can't prove one way or the other. Dark matter is a given example. There were some issues associated with orbits and within a galaxy. So voila, dark matter. Well, we haven't found dark matter. We don't even know whether dark matter exists. And what I'll show you is that it doesn't have to. To get some of the types of observational events that seemed to people to require something like dark matter. So again, I expect you to be skeptical of what I'm going to be telling you. In this first video, I'll be qualitatively discussing the first of the anomalies or the first anomaly that I found that led back to some missed physics, missed Newtonian physics. But then I'm going to give you, in subsequent videos, the tools to be able to validate that. I expect you to validate it. I expect you to be skeptical of me, just as my own skepticism led me to do the research that I did. And then I want you to take the trouble to validate it, and not just to pronounce it, well, that's not the way it is, that's not the physics. I hear that a lot. Well, that violates the law of physics. Well, most of the people who say that don't have a clue as to what the physics is that may be violated, or whether that's even true. Now, what's my background? I'm a PhD physicist, applied physicist. My studies were in nuclear physics and the diagnostics of high-density plasmas. But I started in college as a engineering physicist. And so technology and an inclination towards technology has always been an underpinning to what my interests have been. And consequently, what I did was when I graduated, I went into contract R&D and consulting in the aerospace and defense industry. And we consulted with both commercial and government agencies. Now, one of the things that we did in doing that consulting was look at early sources of science and technologies. The big issue was to avoid technology surprise on the one hand, and the other hand was to enhance ways of carrying out various types of missions. I was part of a program initiated by the government after World War II. Most people are not aware of it, but our modern university, especially that in the experimental or physical side, owes its form to the funding from the government during those early years after the war. The Soviet Union had announced that they were going to have a program where they trained hundreds of thousands of what we now call STEM researchers, science, technology, engineering, and mathematics. It was not lost in the United States that technology was really very important, not only in defense efforts, but also in economic efforts. And not wanting there to be any kind of technological surprises, especially something that might be existential, like the nuclear weapons were, we embarked on a similar program. And we trained thousands of people, PhDs, such as myself, in the STEM areas. At this date, I don't know that there are many of us still active, still curious, still researching things, but I've always done that. So my credentials are that we learned how to vet various elements of science and technology. There were tools that we used and ways of approaching problems. Some of it was laboratory, some of it was analysis. There were a variety of techniques. Some we use today and not even know that they grew out of that era and ways of solving problems. In fact, the whole idea of what they call formal problem solving using things like the Pareto method, I forget what the other names were. They were classified initially. They were so successful in being able to solve problems or identify root causes that they were classified. They became unclassified, as so many things did, starting in the 1960s. So we learned techniques for being able to work with various broad range of the sciences and technologies of the time. Now, with that, in this particular video, I'm going to tell you what it is in that first anomaly that I discovered. It came from a contract I had with DARPA, the Defense Advanced Research Project Agency, and we were looking at trajectories and orbits. And I took a slightly different approach. I was fresh off my PhD, and I was, as they say, loaded with all sorts of new techniques and technologies, not technologies, but ideas and approaches to solving problems. So I took a different approach to solving the orbital problem than had been taken before. In solving that problem, I came up with an anomaly. Well, it was only an anomaly in the sense that that was not something that was recognized or taught within our texts or our coursework. But we validated the fact it was a legitimate approach. Now, we abandoned it because, as I will describe later in the next video, It turns out not to have been relevant to the contract itself. It was an interesting finding, but it had more impact down the road in terms of physics itself than we imagined. And 10 years ago, when I started to look into it, I began to realize what impact it could have. And it formed the basis of the hypothesis that modern physics may in fact be in trouble. So, with that, I'm going to talk about, at least qualitatively, the first anomaly. And again, to me it was an anomaly at the time, and to everyone else I'm talking to now it's an anomaly, but it's not an anomaly. It's actually a deeper first principle than we normally use. We normally think we use first principles when we do various types of analyses, but we don't. We use what I call derived principles. They're at a level above. We've already made our assumptions and we've come to kind of our approaches based on that, leaving behind the deeper first principle approach. So, that anomaly grew out of looking at an orbit and not using the center of mass approach. Now, if you look at a complicated object like this, it's got a mass here, each taken to be a point mass at the end of a massless connecting rod. And when we look at orbits, our traditional approaches are that we take these two masses and sum them up and put them at the center of mass of the object. And when we do the calculations of what's called the orbital angular momentum, we take the radius of curvature of this object, which for masses, that center of curvature is called the barycenter. This radius of curvature times the mass times the angular rate of the object gives us our orbital angular momentum. That's our traditional approach. A more formal approach is to look at this thing as made up of two masses. And these two masses, m1 plus m2, sum up to the center of mass. But now if we look at the orbital angular momentum in the object, I'll orient it this way, because if you orient it other ways, you don't pick up an anomaly. But if you orient it this way, what happens is you have mass 1 and a new radius of curvature, and you have a second mass and a second radius of curvature, both objects moving at the same angular rate, and so you have one angular momentum, orbital angular momentum, a second angular orbital momentum, and when you sum them up, they don't equal the sum of the orbital angular momentum from the center of mass of the object itself. That was the anomaly. Now, does it make a difference? In certain instances. In other instances, it does not. For man-made objects or small objects moving relative to large objects, it doesn't make any difference. Our approach to using the center of mass is good. It works very, very well, and we don't really see any deviations. But for academic purposes, if you look at objects of comparable size, what comes to mind is the Earth-Moon system. The models we see, some of them absolutely beautiful computer graphics of how the moon was formed when Earth was struck by, where the proto-Earth was struck by a planetesimal the size of Mars. They collided, shattered, vaporized one another, and then the moon condensed out. And those are lovely to look at. But they're wrong, because when you take two objects of similar size that are interacting gravitationally, that is, the orbital angular momentum associated with those collisions is not given by the center of mass. It's far larger, far more complicated. So, beautiful to look at, but wrong. So, with that, what I'm going to do in the next video is I will give you the tools to be able to analytically deal with the issue of how to really calculate the orbital angular momentum. Now, I don't expect you to have all of the things at your fingertips that you may need. I'm going to be using algebra as much as possible. There'll be some calculus, but for most purposes, calculus is just a way of summing things up. The equation that I used to calculate the orbit, it was the Euler-Lagrange equation, which is a very sophisticated approach. In fact, it's the equation that Einstein modified for his general relativity. But it's a good classical equation. But it's complex, and part of that complexity is that the orbital angular momentum is a requirement. Now, we can do it with a center of mass, like we currently do it, or we can do it using a modified, more exact first principle form that I will be describing. If you don't have a background in math or calculus or even physics, there are some articles in Wikipedia that are very useful. YouTube has a great many videos that are also very useful. But you can very quickly get beyond the scope of what most people are willing to put the time and effort in on. So, trust but verify. Verify as much as you can. Don't be cynical, but do be skeptical. This is Luther Name. Be sure to post any comments that you have. And thank you for watching, and I'll be posting a new video shortly.